today. I guess I wanted to talk a little bit, I mean, as usual, just about the quiz, if there are any issues with it, and also, I guess, the assignment, which was due last night. Did most people, I assume most people would have done it recursively. That was kind of the intention, although I didn't actually, I don't think explicitly, I don't know if I explicitly said it had to be recursively, but that was kind of the idea that I had.
Yeah, Anthony, I think there was a way to do it non-recursively and still
Yeah,
have at least with my implementation, I think I had a big O of n implementation. Whereas recursive, I believe it would be n log n.
yeah, and that's why, that's great. So you can do it. I just, for me, kind of breaking it down into subarrays and subarrays just made sense recursively, but certainly you didn't have to do it recursively. Oh yeah, it's not due. Sorry, I'm used to them being due on Monday. I forgot that this one is a little bit further back. At least I think. Oh yeah, it's due a couple days. Sorry, the other ones were due on Monday. I forgot this one in the schedule, so on my little calendar it was due today, or last night, but it is due in a couple days. Sorry about that. Yeah, so again, for those of you that haven't started the last question, there's a programming question that doesn't have to be done recursively, and it sounds like Jacob found a really, I think it was Jacob, yeah, found a really good solution that wasn't recursive. But again, when I just kind of drew it out, for me, recursive work, but again, it doesn't have to. We're having a meeting. I think it's actually yeah, today. It's on the 16th. Yeah, I'm having a meeting with a couple of other instructors just to kind of discuss some things. I mean, it turns out there is a lot of flexibility, and it kind of depends. I mean, I think I can mostly make the call. Like I was mostly just worried about if there was university or department regulations that I couldn't, in terms of how the weight, if I want to shift weight or scale or anything like that, because I haven't actually had to do that here yet. I think the two things I'm considering are again, obviously scaling it, so, or just lowering the number that's out of, so instead of the exam being out of 45, maybe make it out of, I don't know, 38 or something like that. I'd have to kind of think about which number, but again, I think somewhere in the mid to high 30s seemed like it seemed a bit better. But and another thing I've been thinking about, and again, I can discuss this, I'll probably discuss the options with you after this meeting, is making it so, well, I guess, so there's three other options. Option two would be to allow you to shift the weight, so midterm one was worth less and your other midterms are worth more. And I guess the other option I've been kind of thinking about and just kind of playing with the numbers a little bit is allowing you to actually improve your midterm grade based on the grades of your other exams. So like, let's say you got 60 on midterm one, and your midterm one score after so your midterm one score changes to be your midterm one plus your midterm 2 over 2. So then if in midterm 2 you do a lot better and you get a 90, again, 60 plus 90 over 2 is 75. That would change it so your midterm 1 now goes up to 75. So if you can kind of show that I mean, a lot of these concepts build off of each other. If you can show that, no, you understand this stuff and you're able to kind of demonstrate that better in the second midterm, it could rise to the weighted average of your other exams. Yeah, and I think midterm 2, I've learned a little bit of things from this, and I think the format will be hopefully shorter. Yeah, but instead of just having, I'm actually saying that your midterm 1 score would be this, as opposed, so yeah, your midterm 1 score just goes up to 75. So then instead of your midterm 1 being 60 and your midterm 2 being 90 and the average being 75, the average now would be quite different. It would now be 75 plus 90. So now the average, instead of being 75, is actually 82.5, right? Because I think, and why I'm thinking about this third one is, again, I think if, again, I want to be fair to people that across the whole grade spectrum, right? So there are people that did, I mean, I'm sure everyone wants a better grade, but I'm sure there are people that did quite well. And again, if I make midterm twos, again, if I give the option to have midterm two worth more, that's can actually just be a straight up bad option for people that did really well in the first midterm. So I think if we do like a weighted average, then it can be, I guess I could say that the people could do it either way. So I guess both of your exams could improve to the weighted average. So again, if for someone that got like a 90 on the first midterm and they kind of do a little bit worse in the second one, their midterm two could be pulled up. So again, it's something that at least is somewhat fair for both, where I kind of use this weighted average and can pull an exam up for all the people. Yeah, I do think that's for the people that, again, because there are a lot of people kind of in the 50s and 60s that I feel like if the next exam has a higher average, this is a way of incentivizing again people to work hard and do better on this next one. And the next one obviously isn't going to be as much proofs. I think I can do the next one online a little bit better if it's kind of some kind of doing some visual data structure stuff and some sorting stuff, and I mean just asking what the differences between different sorting algorithms and stuff like that. I guess the thing with the third one is that the weighted average could work both ways. So it could work for people. I could say that your lowest midterm is going to go up to the weighted average of them. So again, people that did really well on midterm one, I mean, obviously I still want them to do well on midterm two, but it's still something that if they don't, if they make a mistake on this or screw up some way, they can still get this weighted average benefit. It's just simply shipping the weight to midterm two is just not fair to the people that actually did really well in midterm one. But yeah, it's something I'm going to talk about this with other instructors and just make sure that this is something I'd be allowed to do, and then I'll kind of talk to all of you about it as well. But yeah, I do think again, it was my first time teaching a discrete math unit. Again, when I taught this course at UBC, it was really just data structures and algorithms. So I've got more experience with those types of questions, and in some of the courses that they have kind of online quizzes. So I've seen the types of, at least I have more experience with what it seems like has worked and hasn't worked. Whereas I do think the discrete math stuff ended up being way more time consuming than I expected for the first one. So I hope that for the second one, I can shift it so it's less of a time pressure. I mean, with still having questions that are difficult, or at least a range of questions. So it's not just going to be that it's going to be a midterm two is just going to be trivially easy, but I'm hoping it'll be less of a, I feel like I could have done it, but I didn't have time, versus everything I knew I was able to show. Any other questions? Yeah, I can see maybe. But sometimes the things I think are fun aren't that fun. So if I try to add a fun bonus question, it might not be that fun or bonusy. Like I thought the last question on this midterm was a cool way of doing recurrence relation, but with drawing all the circles, but it turns out it wasn't that fun. So last day, I believe we basically completed doing all of our analysis for merge sort. And I'll post the solution after, but I did want to talk a little bit about the, I guess, depth of the recursion on the bottom right side. So let me move my tablet over a little bit. So there's a couple things I want to talk about, and because this is, I guess, a visual way of just thinking about merge sort here in the bottom right corner. So again, we know here what this is saying is that we're kind of splitting this array into two halves. And it was as simple as just saying elements in the first half go into this first subarray, elements in the second half go into the second subarray. So I think hopefully we can see that this is going to just take O of n time. Again, we're looping through the original array and going through all n elements and saying put half of them into this and put half of them into that. But again, what might not be as obvious is this takes O of n time as well. Because what's happening is we're going through to split, I guess, if this is array and this is kind of subarray A1 and A2, to split A1, it's going to take n over 2 of our total elements to split in half. And this is going to take another n over 2 to split into these 4 quadrants. So each kind of split, we're actually going through all n elements of our array, even though it's in 2 separate halves, and putting them into smaller arrays. But if we think about the total number of elements I need to visit to split both of my n over 2 sized arrays is going to be n. So at each one of these, it's O of n time for each split. Because we're splitting 2 n over 2 arrays, and then 4 n over 4 arrays, and 8 n over 8 arrays. So that's why I've got this time per level as O of n here. And I guess if we think about the number of splits that take place, we can kind of think of this as the size of the array here is n to the 2 over 0, which is this is just an array, but yeah, it does have a tree structure. And that's because the number of elements in this array is n over 2 to the 0, which is just n. Whereas here we see it's n over 2 to the 1. Whereas here we see all the array sizes are n over 2 to the 2. So on each, if we think about the number of times we're going to have to split until we get to our base case, remember our base case when we stop our splitting is when the arrays have a single element. We can think about the fact that it's going to keep splitting and splitting and splitting. The next time it's going to be n over 2 to the 3. They're going to be n over 4 sized arrays. And I guess what I can write down here is that after I splits, so after 1 split, we had n over 2 to the 1. After 2 splits, our array sizes were n over 2 to the 2. So after I splits, array sizes are 2 over 2 to the I. What we want is we want to think about, okay, well, how many splits will we get to our base case? So if we say that if the to the I split is when we get to our base case, then we want to solve for to the I equal to n. And what we're going to see there is, if we solve for I, we're going to see that I is log of n. So if the number of times we have to split and split and split and split eventually gets us I iterations, the maximum number of times we're going to have to split is going to be bound by log n. And that's why, again, when we were talking about our running times over here, which is over on the left side of the screen, we see that no matter what, this is always going to be n log n, because again, at each level of this tree over here, we see that it's going to take O of n work to kind of go through all the elements of an array at a certain level of this visual representation. But again, the number of times we're going to actually have to do this process of going and doing this split or this merge is bound by log n. So what we can say is the number of times we split and merge is going to be bound by log n. And each level of split or merges takes O of n. We're going through at each one of these levels, we're either splitting n over 4 times or merging n over 4 sized arrays, going through them to merge them into 2 n over 2s. And in fact, it's actually going to be 2n log n, because again, we're going to have log n splits and then another log n merges. And each of the splits and merges is going to take O of n time, but both of those are going to be bound by log of n. So again, we're going to have log n splits and then log n merges, but that's still going to be big O of n log n. I'm not sure what you mean by the left half of the screen. I'm actually like, everything on kind of the left of the purple line is actually just white space because I've zoomed into the document so much. I'm not sure if that was what was confusing maybe. But this is just another way. I mean, we kind of did the proof and we last day and we kind of came up with this n log n. But this is just a visual way of showing it. The textbook kind of, it has this image is from the textbook, and it kind of in the caption just says, here's a visual representation of showing the fact that at each level, O of n work happens, but the number of times that we'll have to do this work is bound by log n. So therefore, visually, we can see that we'd expect the total running time, again, to be O of n log n. Does that make sense? And this is why for the assignment, for those of you who are doing it, why the recursive version, and that's why I said, yeah, if possible, I'd like you to try and go for an n log n time, because what you're doing is you are splitting the array as well into n over 2 size chunks. You're you're actually, so again, if it's going to be some variant of n log n, that's kind of what we expected for full marks. And it sounds like some of you have actually got better implementations, which is great. But as opposed to, again, kind of doing some sort of, I guess, brute force way of seeing if the two different, you're comparing two different arrays in the last problem in the assignment, instead of some brute force method, which is going to be doing it in n squared or n cubed or something worse. So again, if you can get the correct result, you'll get a number of marks, but there are some marks associated with whether or not you can do it in an n log n time or better. Any other questions about this? Okay, so again, what I wanted to move over to do is now also the Quicksort one, which is, again, I know some of you like PDF, some of you like document. I'll just open it here and annotate it on this screen. Probably. I mean, if you document it and explain why you think that your R strictly better than an n squared, I'm sure the grader can take that into consideration. So I guess from I guess fairly zoomed out view, we see that the Quicksort algorithm here that I showed off in the slides in the videos last week, again, really just says we've got, oh, sorry, this should be L and R. I should remove that. But we want to, we're again going to somehow, and there's a whole bunch of different, the interesting thing about Quicksort is that there's a whole bunch of different ways you can partition these two, I guess, two sides, or get a pivot and put elements on either side of it. And that really, really affects both how much memory is being used and often, I guess, more if the pivot is chosen well, the running time of the algorithm. But essentially what you're doing is you're saying, I'm going to, I guess, pick some pivot. I'm going to put everything on, all the lower values on one side of it, all the greater values on the other side. And then I'm going to call this recursively to then just do a quicksort on the left half of the array and the right half of the array. So what's happening is you're just calling this recursively and saying, I want to sort the same array, but within that array, I'm only sorting from indexes, the same low index up to one before the pivot, and from one index past the pivot all the way to the right side. So starting at a big array, you're going to, again, put the pivot somewhere, hopefully near the middle. You're going to make sure everything over here have value less than the pivot. Everything over here is going to be greater than the pivot. And this was your original low and left and right. You're going to say, okay, now I'm going to call recursively quicksort on with the same low and p minus 1. So you're going to quicksort this array, and you're also going to quicksort this array from p plus 1 up to r. And then from here, that's going to do the same thing. They're going to pick a pivot and then recursively do both halves of that array. This is going to pick a pivot somewhere and recursively. So again, it's the same as merge sort, where we're getting smaller and smaller arrays where we're picking a pivot in at each time. But the main difference here is, again, you can create two separate arrays like merge sort does, or one of the techniques I showed off with this in-place quicksort is you can actually just, in this array that you begin with, swap elements around so that all the values are less than the pivot. The pivot's somewhere in the middle, and there's another set of the section of the array where all the values are greater than the pivot. And you don't have to temporarily make other arrays to recurse over. instead you can just use indexes within the original array and just look at those regions of the array in your recursive calls. So you're always working with the same original array, but you're just looking at different regions within that array in each recursive call. Does that make sense? So I guess the first iteration of Quicksort might be to just do it almost the same as merge sort and just create new arrays. But then the improvement I talked about was this in-place Quicksort, where again you're shuffling around the original array and just looking at different regions of it. No, so I think in the labs this week I think they'll choose just the actual index that's in the middle of that region, as opposed to the last index. But there are a lot of different ways. I think a lot of Quicksort algorithms actually just say, okay, this is the range. I'm looking at this region of the array. I'm just going to at random choose an index within this range and set that as the pivot. So they always choose a random number. And that typically, again, even if arrays are sorted or reverse sorted, that typically, again, almost always still gets n log n running time. Again, some algorithms will take the first and the last or the first, the last, and the middle, and just take the median of those three values, which again, you can still do in constant time. I guess the idea is that you'd like to spend as little time as possible choosing the pivot and just try to make sure it's not the maximum or minimum element. And there are a lot of different variations to do that. Does that make sense? Yeah. So I guess in terms of the proof of the running time for this, what we're going to have is, again, the base case, similar to merge sort. We kind of see that we've got a base case here. Then we've got to do this partition where we're going to actually go through the whole array, which is going to take n. And then we've got hopefully something like two sets of roughly t of n over 2. So again, I think if we do our proof by substitution, the substitution to get this will be very similar to the same as merge sort. We've got a base case that's going to be something very similar, typically just a single comparison. Then you're also going to have to do something that takes time n, because you're going through all the arrays or all the elements in the array and determining which side of the pivot they have to be shifted to. And in basically all different partitioning algorithms, you're going to have to do this, where you're at least going through all the elements because you have to make sure that all the elements less than the pivot are on one side and all the elements greater than the pivot are on the other side. And then typically, again, this isn't always going to be n over 2, but the two of these together are going to obviously add up to about, like instead of being 2n over 2s, it's going to be 2 of something that ends up to essentially n minus 1. So you're going to be calling this recursively with two things that are almost add up to that whole array, because you're always just missing, your array is always at minimum going down by at least size n minus 1, but up to n over 2. So, and why I'm moving a little bit further through this is because we've kind of already, in some ways in the slides, talked about how, again, the best case is going to be the exact same as merge sort, because it's going to have the same structure where, again, we can break it down to that same tree I showed you at the beginning of the day, where each level of splits is going to take, each level is going to take O of n. And the idea here is that if you break it up into roughly, again, 2n over 2s, then 4n over 4s, then 8 over 8n's, and this is going to be roughly bound by log n. We see that with Quicksort, the main difference here is that it's probably going to be I mean, the depth is probably going to be a little bit worse than strictly log n, because again, this is often going to be like an n over, the n over 2 and n over 2 might not be strictly n over 2. Like on our strictly level, on our first level, it might not be that you pick a pivot right in the middle. It might be like, I don't know, 3n over 8 and 5n over 8 or something like that. But what we see is that the depth of how many splits we're going to do is always going to be log n plus a couple more, but it's going to be still, again, within the range of log n, unless you're always picking the worst element. And then you're obviously going to have, if you're just getting rid of one value each time, then this depth is going to just be n minus 1, because you're going through it n times, and you're only getting rid of one each time. But what we'll see is that the average and the best case are actually both n log n. And it's only the worst case that is n squared. And we saw that in the slides, that's when you pick either the minimum or maximum element. And then it looks something like selection sort, where we're just saying, oh, this pivot is here, everything else is going on the other side of it. I'm taking the next smallest pivot, everything's going on one side of it. The next pivot, everything's going on one side of it, which, again, in terms of how many pivots you're getting into the rightful location each time, is really the same as in selection sort. And so, yeah, in very unique scenarios, it is n squared, but I think almost all real implementation of Quicksorts aren't n squared, because again, just the way you're picking the pivot, you can usually avoid making sure you're picking either the largest or smallest ranked element in that part of the array by various methods, which we've talked about a few of them. In terms of stability, again, it kind of depends on the partitioning. I'll say that yes, but I'll say, but it depends on the partitioning technique used. And so it depends first how the pivot is chosen. And also how the swaps are done. And so the one we saw in the videos, I don't think, which one did I show? I don't think the one in the videos was stable, because I think, again, you pick the pivot on the very right side, and you moved your L's and R's into the middle. And then at the end, you swap the pivot with the L. So again, doing that swap could actually break stability. But what I'm going to show is we're on the right side over here, we are going to see another one, another version of choosing this partition that again is in place and again has a lot of similarities. But I'm going to show the kind of the simplicity of this whole quicksort algorithm and talk a little bit about why it's commonly used over merge sort. So again, I guess if you think about quicksort as a translation of merge sort, where you are allocating new space for arrays at each level, so you're allocating space for arrays as you do your splits, it would be O then. So I guess I can say if implemented similar to merge sort, it is O of n, but most and close to all implementations are in place, which means that you're doing all the partitioning in the original array, and you're not needing to create any new space, and that is the main reason. This is the main reason Quicksort is used over merge sort. Because that memory allocation ends up being very, very expensive. I'm not sure if for those of you, I'm not sure how many of you have done courses like 230 where you talk about memory accesses and locality and caches and stuff like that. But sometimes, again, memory accesses can be as expensive as millions of operations that a CPU can perform. So if two things are again asymptotically quite similar in terms of runtime, but one is way more memory efficient, it actually ends up not just being better in terms of memory capacity, but also with overall execution speed. Yeah, so this just means as the size of the input increases, how much additional memory besides the array you're given with do you need? And again, we're always going to need a constant amount. We're going to need some local variables. We're going to need like an integer variable for the partition index. But we're not going, like in merge sort, when you need a separate array to temporarily allocate to hold all those elements. Again, that array, again, if you're working with 1 million elements, creating an extra array to hold 1 million elements actually ends up being very expensive from a memory perspective, but also the time it takes to do that allocation and all that stuff ends up being very expensive in terms of runtime speed as well. And so that's the big thing. So again, although they are kind of tied in terms of their average case n log n, in practice, Quicksort is typically much faster because if you're looking beyond just the I guess runtime comparison of the algorithm at a pseudocode level, if you actually think about what's happening in terms of memory usage, that's where the tiebreaker occurs. Does that make sense? Because again, strictly from an algorithm analysis perspective, not thinking about implementation or memory or anything like that, it actually seems strictly worse than merge sort because it's got a worst case. But I guess the idea here is that the worst case can be quite quickly avoided, and quite quickly and easily avoided to almost guarantee it's going to be in the average case, and the fact that it's using much less memory is what in I guess in real world examples it ends up being actually the fastest, and that's why it is called Quicksort. So on the other side of the screen, I just wanted to show you another variation of this that is both, it's again, the whole algorithm here is shown right here. There's not even any helper methods, and it's quite simple. And in fact, the implementation of this is, I think, one of the quickest and easiest implementations of Quicksort, because you've essentially got a base case at the beginning, you've got two recursive calls, and then this whole thing in the middle can actually be broken down into a single, like, if a of I like this whole for loop, the only thing it's got is this for loop that has all this stuff in it, but that can be written, that is, I mean, commonly written in a single line where it's just saying, if this, then swap that. And I mean, you're incrementing the P in the single line, because when you do plus plus P, it's going to first increment this value, and then get the incremented value as the index in the array. So this algorithm is something that's, again, typically like 1, 2, 3, 4, 5 lines with the recursive calls at the bottom. So it's something that's done really, really. The code itself is quite small, and it's because some of those lines are actually the recursive calls in the base case, and it's in place. And again, this is a variation which is just taking the lowest element in the range as the pivot. But again, you could say, like, make the pivot as the median of low, middle, and high, low or left, middle, and right, and then you could almost guarantee it would never get kind of reach that worst case as well. So yeah, that's what we're going to do here. We're going to show that it actually is in place as well. So let's assume this is the original array. How am I going to do this? I want to be able to see the algorithm. Okay. So this is the original array, and we know that, so I guess our array is this whole array here. The L and the R are the indexes. So again, we'd call this like Bentley Quicksort. We'd give it the array, and we'd give it index 0 and n minus 1, where n is the number of elements to start. We're saying originally we're going to give it a whole array. Our left index is going to be the very first element. Our right index is going to be the very right element. And we're going to just walk through this algorithm really quickly with this array. So I'll scroll down a little bit just past maybe the input and output lines, so I can see all the algorithm, but also see all of the So what we've got here is we've got L, we've got R, which are the leftmost and the rightmost indexes of this I guess current array. This actually could have been, this might be a recursive call. There might actually be other things in the array that are this could be the result of a recursive call, for all we know. Let's assume this is our original array. So what we've got here is we're saying P is the pivot. So this is always going to be the pivot here. Maybe I'll just color that blue. And we're looping through, our I is looping through, oh, not the last line. Our I is looping through every index from one higher than the low. So again, one higher than the low, up to and including the R, or the left and right, sorry. I think of it as low index and high index. But the left index, so starts one above the left index, and as we can see, it iterates all the way to through all the indexes in this region of the of the array we're looking at. So what we're going to do is we're saying if, and so we know that L is the pivot. I guess this line could also just be P here. But if if this value here is less than the pivot, then I'm going to move the pivot one forward and then swap them. So I'm going to say the pivot index is going to be one forward. So P is now going to be here. And I'm going to swap the index at P and I. So really what we're doing here is just swapping this forward. There's nothing to swap it with, but we'll see in later iterations, we'll actually swap it with something. So again, now we've still got a -4 here. Now I is going to go to the next index. We're saying, is this less than the, oh yeah, it has to be now. Is this 6 less than 2? No, it's not. So we're just going to go to the next index. So we're keeping the -4 and the 6 here. And now I is at index 0, 1, 2, 3, or whatever index we're in. This, again, this could be a different subregion of the array. And we're saying, is the 1 less than 2? Yes, it is. So then I need to, again, move the P forward 1 to here, and then I'm going to swap. So what's going to happen is -4 is going to be here, the pivot's going to be here, but we swap the 1 and the 6. So now I goes to the next spot. We're saying, is this less than the pivot? No. I is going to go to the next spot. We're going to say, is -3 less than the pivot? So I'm going to put ticks here every time we find one that we need to swap. So here's another time where we need to swap. So again, 3 is less than -2. So again, our P is going to go forward 1. And we currently have -4, 1, 6, and 5 here. We know that we're going to have to swap these two, which is going to leave us with -4, 1, -3, 5, 6. Oh, sorry, I went down a line for no reason. It's going to leave us with -4, 1, not 6, -3, 5, and 6 in the eyes here. We're going to now say, is this less than the pivot? No. Is 7 less than the pivot? No. So what we're going to do now is, now we get to the end. And when we break out of this loop here up at the top, we see now we just swap the low index with the pivot. So we're just going to say, now we're going to swap. Where's our P? Our P is right here. We're going to swap P and 2, which is going to end up with a -3, a -4, a 1, a 2, a 5, a 6, and a 3. Or maybe I'll write this as the blue. And now we've got 2 sections of the array. The green is going to be, in the green, all are less than the pivot. So we're going to call Bentley Quicksort from the low index, which is L, up to P -1. And on the right side, we're going to start at P +1 and go all the way to the right index. So that's that second recursive call. And then each of these are just going to do the same process where it swaps, or it moves the pivot from the left side to the middle based on how many elements in that particular thing it's greater than. So what we really did is this P that we kept moving forward whenever we found an item that was which was smaller than the pivot. What we did is we moved the pivot forward based on how many values we found less than it, because then we got the pivot into its correct location after we had visited all of the elements here. So this one is in place because, again, we just said, let's start the pivot at the left and let's think about how many values in this region of the array that I'm searching for, that I'm responsible for, which again, the next iteration of the recursive call is going to be the green or the red. How many in this region do I have to push the pivot past so it's in its rightful place? And then I know that everything that I pass is less than it. Everything on that I haven't passed is going to be greater than it. So that I can call the recursion on those two sub-regions. So this algorithm right here is a working, it is the full quicksort, where this is where the partitioning happens right here. So that's the kind of the partition step, and then it just calls the recursion on the two different subarrays that are less than and greater than. It is this is an good question. It is an L here. And it's an L because we're always comparing it with the two. We're always comparing it with the two at each iteration. And because the P is just how many values we've found that are greater than that two. And so again, the P is the index of P is at different places at different times. Sorry, I missed one P here. It stayed at index 2 here. Oh no, it was here. But the low is what is the index holding the actual pivot. If it just contained two of the same element, it would not do any swaps, and it would just say this one's the pivot, the other one's higher than it, and then in the next iteration of the quicksort, it would be trivially sorted. Because the next thing, the left, when it calls the recursion on the other region that's just got a single element, our L and our R indexes, which I'm circling at the top here, would be the same, so it would return. So similar to merge sort, this keeps creating two sub-regions, but in place without actually using an additional array, and until our sub-regions, the range that we're looking in this part of the array is just a single element. Any questions about this? 1025. Okay. So thanks. Yeah, good luck working on your assignment. I forgot that it was extended. I will help. So I'll have office hours that I can help you out with it tomorrow. And again, I'm hoping the worksheets will now be more or less caught up from the videos from now on. We're going to talk about one more sorting algorithm, which I'll introduce in the videos, that requires, again, the understanding of some of that tree terminology, especially, I guess, the concept of a complete tree. So based on that, we're going to go through one more sorting algorithm, and then we're going to move deeper into the tree unit. Thanks. I'll stick around for questions for a few minutes, but I'll stop the recording now.
The recording has stopped.